Alrighty, so we're looking at relative velocities. This is not how fast your family can run. Thank you, Tony. Although I'm always amused when I say that, relative velocities, and then over here on the right-hand side, what does it say? Family race. See? It's funny. Physicists have a sense of humor. It's not just me. So, Tarzan and Tarzana. Tarzan and Tarzana are brawny ape people. I don't know what that means. Does it mean that they are apes that are like people? Does it mean they were raised by apes? Do they resemble apes? What exactly does it mean that they're brawny? I don't know. Page 95. Page 95. Page 219 was the last class that I just taught. Page 95. So Tarzan and Tarzan are brawny ape people. They decide to have a race across the river. Both are excellent swimmers and have the same ability, which means they can swim at the same rate. If they're going to race, they would end up tied. If you think they'd know that, they wouldn't bother racing. Tarzan swims straight across, landing on shore directly across from where he started. And you can see his picture there over on the left. Tarzana jumps in and points herself across the river, but ends up further downstream when she reaches the other side. What did he do compared to her?
He adjusted for the water.
He adjusted for the current. She went straight across and ended up downstream. Okay, so those are the two on the left there. Who finished first, do you think? Who got there in a short amount of time?
Probably Drill, but she wasn't at the actual race.
Okay, well, we'll see. And then there was Cheetah, faithful, brawny ape pet.
That makes a very good pet.
Is he an ape? Or is he a cheetah? And does he need to be brawny to be part of this family? And if they were raised by apes, why is he their pet? Wouldn't he be like their son or brother? It's very weird. See what I mean about this book? He chooses to swim across the same river, but at the same time, or no, at a different time, when the floods were raging and the river flowed at 5 times the velocity it did when Tarzan and Tarzana swam across it. Cheetah, too, is a good swimmer and has the same ability as Tarzan and Tarzana. Did Cheetah finish the crossing in a shorter time? He went farther downstream. Did he finish in a shorter time? What does your gut tell you?
Wait, he finished further downstream?
Yeah, because look at how fast the current's going, right? He ends up way downstream. But did he get across faster? These questions will be answered in this section. So, first of all, relative motion. In trying to answer the posed problem, we first need to define what relative motion is. Suppose you're traveling in a car and are being observed by a highway patrolman sitting by the side of the road as shown in figure 3.25a, which unfortunately is on the next page. Alright, so suppose you're traveling in a car and are being observed by a highway patrolman sitting by the side of the road as shown in figure 3.25a. The patrolman will measure your velocity relative to his position. In this case, the patrolman is not moving. So let's assume the velocity he measures is 140 kilometers an hour. I would never be driving that fast. This would be someone else. Your velocity is said to be 140 kilometers per hour east, measured relative to the ground. Because as you can see in the picture, he's standing still. And this person is foolishly traveling at 140 past him. Now suppose you pass the patrol car with a velocity of 140 kilometers an hour while it's moving with a velocity of 100 in the same direction. Also a bad idea. If a cop car is doing 100, should you pass him doing 140? No! This physicist dude is not very smart. Who would do this?
Not very smart or just really badass.
I guess. I will say that I have been in a car that passed a police car on the highway. He was doing 98. And we came up slowly, we're doing 100, right? And it got to the point where my friend was very frustrated, and I said, I'm passing him. I'm like, are you crazy, man? You don't pass a cop. Right? He's doing 95, he wants us to pass him. Okay, so we pull out, right? He sets the cruise at exactly 100, right? So it took like about a minute to slowly creep past, right? And I'm sitting there in the passenger seat kind of looking, right? And the cop's like, what are you guys doing? Looking at me, right? I'm just sitting there looking forward, right? As soon as we pulled in, he gave us a warning. He said, I was doing 100. If you passed me, you had to be speeding. Like, it took us like 90 seconds to pass you. We might have been doing 100.1. Whatever. It was like ridiculous. Yeah. So then he gives us a warning, says slow down, right? And then like 2 miles later, there's like a town. He pulls in and goes for coffee. Like, see, all you had to do is wait 2 more miles and we would have been past him. So let that be a lesson to you.
Always pass a car.
That makes sense why this guy was going 140.
I guess if you're going to pass a cop, make sure you're going 140, because there's apparently if you're going 100.1, you're going to get pulled over
Get
anyways.
a warning. Get a warning.
All right. So anyways, so this time the velocity is measured at 40 kilometers an hour relative to the patrol car. If you flip the page over and look at the book, right, his radar is going to show up 40 because you have to account for his speed as well, right? Does that make sense? So it's a relative velocity. While the patrol car has a velocity of 0 in its own reference frame, its 100 kilometer an hour velocity must be measured relative to the ground. Notice that your velocity is the same, but the two measurements done by the patrolman are different. The bottom line is that a velocity value is always measured relative to a reference frame. We talked about that in grade 11. In everyday use, we are accustomed to using the ground as a stationary reference frame, even though the ground is clearly rotating as the Earth rotates and orbits around the Sun. This frame is implied in most problem situations. You do not see on the highway speed limit signs maximum speed, 100 kilometers an hour, relative to a stationary Earth. You could try to use that in a court of law. It's not going to work. I've never tried it, but I wouldn't suggest it. Now we can apply. Yeah, I don't know. But fast, man. Like,
Yeah, so like
thousands and thousands. Yeah, just sitting still, you're traveling thousands of kilometers an hour. So what's another 100, right?
Exactly.
Yeah, it's all relative. Now we can apply this knowledge to the swimmer in the river. If Tarzana floats with the current, it will appear to her that she is not moving relative to the water. To actually measure her velocity, someone must stand on shore relative to ground, which is stationary, and watch her go by. In fact, to measure the river's velocity, we must also measure it relative to shore. In order to keep these velocities distinct, we use a series of extremely annoying and frustrating and confusing subscripts.
Someone actually put like an arrow after up and put stupid.
Did they?
Yeah.
I probably told them to do that because they're stupid. Look at the subscripts. VOG, relative velocity of the person or object relative to the ground. VMG, velocity of the medium the person or object is in relative to the ground. And VOM, okay, forget all that nonsense. Okay? Forget all that nonsense.
But I like bomb.
Sounds like a bathroom cleaning supply. Instead of VOG, VR, resultant velocity.
Equals R.
Or just R. No, well, you can write this wherever you want.
CW or
Right in the text.
You can write it right in the textbook if you want, sure. VMG, I would say that is velocity of current or wind. Because generally these type of things happen in rivers or in wind. Current or wind. Let's make it simple. Let's not make it confusing. And now the last one there is VOM. I would suggest velocity of plane, velocity of boat. Because again, if it's going to be things in current or wind, it's going to be things like planes and boats. So let's make it simple. Okay? In this particular case, it's not boats, it's Tarzan and Cheetah. Call it what it is. Now remember, in all cases, the resultant is always, and we talked about this yesterday, the resultant is the boat plus the current. These are all vectors. Or the resultant is the plane plus the wind. Right? Those are the two that you sort of need to know. Okay. Let's move on to Tarzan and Tarzana here. Okay, so, why does that say case 3? I don't want case 3. I had the wrong word. Okay, so, example number 7. In one dimension, this is relative motion one dimension. In one dimension, the river problem has 3 possible cases, shown in figure 326. When the river flows, its velocity is 1 meter per second east. Tarzana can swim at 2 meters per second in still water. So there are 3 cases. 1, there's no current. It's a lake. Case 2, I suppose. Tarzana swims with the current because the dam broke. And case 3, Tarzana swims against the current. Right? So there's 3 things. So, assuming everything is east and positive and nice and everything, right? So we would add the overall resultant. Let's just say resultant is Tarzana plus current. Let's just do that. Okay? Resultant is Tarzana plus current. So because there's no current, the resultant is going to be 2 plus 0. And because it's one dimension, do I need to add any angles here?
No.
No, of course not, right? Because it's like that. It's just that, 2, right? Like it's just 2. Her resultant is 2 because that's the only vector that we're talking about here.
So 2 meters per second.
2 meters per second, right? Now, case 2 is with the current. Once again, resultant is Tarzana plus the current. She's traveling at 2. The current is pushing her at 1, giving you a resultant of 3. And again, because they're collinear, i.e. in the same line, I don't need any Pythagoras, I don't need any components, I don't need any of that, because it's just 2 plus 1 equal to 3. Right? Pretty straightforward. And obviously, if we're against the current, then it's going to be two plus, because it's against the current, minus 1. Do they have 2 plus minus 1, or they have minus 2 plus 1? Yes. Assuming the opposite way, right? Giving you a resultant of minus 1. Okay. You guys can do all that, right? I know you can do that. No problem. That's really just a review. The top of page 99. That's where they show you how to add vectors. That was like an entire 3 days in grade 11, the top of this page. That's why I don't use this textbook in grade 11, because it's not going to work. Okay? So you can see there they show you the head to tail stuff. You can see in all 4 of those pictures on the top of page 99, which one is the resultant, which arrow. There's 2 red ones and one that's sort of like a stripy one.
Straw-looking one.
Yeah, the stripy one is the result, right? You can see the head to tail pattern there, right? Everybody remembers tip to tail, head to tail? Yes? Right? Okay. So let's just go straight to example 8. Relative motion in 2 dimensions. Case number 1. Assume Tarzan can swim at 2 meters per second. The current is 1 meter per second east. And Tarzan is seen to swim directly across. In other words, someone standing on shore sees him going straight across even though the current is pushing him sideways. Why do they see him going straight across? Because he's actually doing what? He's adjusting. He's making a heading into the current and allowing it to him sort of push him back to straight. Right? Yeah, okay. So what does that picture look like? Tarzan swims at 2. The current is 1. So it's going to be a picture like this, right? Here's Tarzan swimming at 2. The current is 1. And he's seen to be going straight across. There's the resultant right there. Is this a right triangle? You have to assume the current is perpendicular to the river type of thing, right? So, yeah. So you would have here, in this case here, you would have t squared is equal to r squared plus c squared. Most of the time, the resultant is the hypotenuse, so you have to be careful here a little bit. Tarzan squared is 2 squared. Resultant squared, the current is 1 squared. So r squared is going to be 2 squared minus 1 squared. And r equals 4 minus 1, the square root of 3, I think, right? .7 meters per second. Tarzan must not only be a brawny 8 person, but he almost needs to understand trigonometry. Because for him to go directly across, he would have to know exactly what? He would have to know how fast the current's going, and he'd also have to know how fast he can swim, and he'd also have to know what angle to angle himself. He might try, he might get lucky, right? But for him to know exactly what direction to head so that he goes straight across, he would have to know that angle.
Probably do it on the go.
Yeah, just readjust as they go. That's actually what airplane pilots do, right? Yeah. They don't set their course ahead. They sort of figure out where they are and what the wind is and where they have to go from. They make adjustments as they go. Yeah. Okay, so theta here is going to be the inverse tan of opposite over adjacent. So that's going to be 1 over. Now remember, the adjacent is this one here, so it's actually 1 over 1.7, isn't it, right? So theta opposite over adjacent. Could I use opposite and hypotenuse? Could I use inverse sine? Sure, why not, right? It's going to give you the same thing. We just sort of get in the habit of using tangent because that's what we always use, so I'm going to use the 1.7. Regardless, they use sine in the book, actually. They get 30 degrees. I'm guessing 1 over 1.7 doesn't give you exactly 30 degrees. Okay, yeah. Now that would be, if this is east, if right is east and this is north, then I guess that would be north 30 west, wouldn't it be, right? No, west, to the left, right?
Oh, wow.
Yeah, this one. Now, case 2, Tarzana swims at 2 meters per second. The current's 1, but she doesn't account for the current. She just sort of starts swimming and doesn't care about where she ends up. So her picture is going to look like this. Blue, red, black, resultant, Tarzana, current. I don't think there was ever a Tarzana in the movies. Her name was Jane, if I'm not mistaken. You'd think that Tarzan 2 would be copyright, or maybe it's in the public domain now. I don't know. Just to find out? Yeah. See if there's any physics going on in there. I think we should watch Gravity because it was so many awards, right? And then I haven't seen that.
It's a good movie. No, it's a really good movie. Yeah, but I watched it in 3D and it was actually like nauseating.
Oh, really?
What if it was actually...
You're in 3D and all it is her like moving around in space, so she's like spinning and you're like...
You need a grab all, yeah. You didn't have a frame of reference, right?
2 hours of free one.
Okay, so what do we got here? I got r squared is going to be t squared plus c squared here. She swims at 2, 1 squared. Oh, yeah?
Oh my god,
So now we're talking about the square root of 5.
all animation. All of it. So like, it would have been so hard for her to do that.
So her resultant speed is actually considerably faster. 2.2. She's going with the current, right? She's allowing the current to sort of add to hers, whereas his is sort of subtracting type thing. Okay. Does this tell us, though, who gets across faster? Your gut might be saying, well, she's going, her resultant is 2.2, his resultant is only 1.7, right?
She goes farther.
But she goes farther, exactly.
Distance now?
Well, we'll get there, right? Let's go case 3, which is Cheetah, the crazy 8 pet.
Wait, what's the, you don't want to do the angle or anything?
Oh, yeah, angle. I do want to do the angle. Sorry.
Who's even teaching this class?
Leaving you hanging there. Opposite over adjacent, right? So that would be 1 over. Adjacent here is Tarzana 2. 27 degrees. Does that surprise you that that angle is different than that angle? No? Okay. So that's going to be east. No, it's not going to be east. It's going to be north 27 east, right? Okay. What is your gut telling you about Cheetah? Is he going to be actually swimming faster?
No, current
Sorry, will his resultant velocity be greater?
Well, yeah.
He goes at 2 meters per second, straight across. Oh, I think blue was the person. Right? The current is now crazy like this. 2, 5. I want to be black. Resultant. You should realize the resultant's going to be way more, right? Resultant squared is, oh no, it's cheetah squared. Big C for cheetah, little c for current. Yeah, especially C is a hard one, right? Okay. So the resultant squared here is going to be, cheetah is 2 squared, the current is 5 squared. So the resultant's going to be the square root of 4 plus 25, 29. He's going to be traveling at 5.4 meters per second at a very large angle. Opposite over adjacent, 5 over 2. 68. That's north, 68 east. Again, we still don't know, though, who gets there first. Who gets to the other side first? Because cheetah clearly travels a whole lot farther, doesn't he? Or she, whatever he is, or she. Yes. Okay, so finding the time to cross. Page 101. In all 3 cases, the diagrams could have been constructed by setting a scale, blah, blah, blah. Okay, find the time to cross. So who finishes first in this race? To find out, we need to look at the 3 vector diagrams which are shown together in figure 3.35. The equation v equals d over t, rearranged to find time, becomes t equals d over v, and we need to find out which v to use. If you look at the diagrams in 3.35, the velocity vector that points in the direction of the desired motion, north, is the appropriate choice. The other vectors involve the motion of the current, which does nothing to help anyone cross the other side, right? If they weren't swimming at all, they would just end up going downstream forever, right? So it's only the velocity straight across that matters. It's not actually the resultant that matters.
We did all that work.
Basically. Tarzan.
Which is the one that matters?
Which is what?
The one that matters?
The one that matters is only the one that goes straight across, because that determines how fast it takes you to go across. Right? The other ones, the 5 here, and the, oh, where was it?
Oh, yeah, that makes sense.
Right? Right? And the 1 here, and the 1 here don't do anything for going across. It's only the vectors that go straight across that matter. So here, it's Tarzan's 1.7 that matters. It's Tarzana's 2 that matters. And it's cheetah's 2 that matters. So who gets there first?
So the river they're actually crossing the river or going down it?
No, the race is to see who gets to the other side, not caring where you end up.
I'm just trying to figure out the target of the cheetah. Which one is?
Cheetah ends up way downstream, right?
Yeah.
But their race is to see who gets to the other side first. Let me finish reading this, and then I think it'll make sense.
That's the curve.
Okay? So, the other vectors involve the motion of the current, which does nothing to help anyone cross to the other side. Tarzan swims at 1.7 in the north direction. Right? 1.7, the resultant. Notice that for Tarzan and cheetah, the velocity directed north is both 2. The blue one here is 2. The blue one here is 2 as well. Thus, Tarzan finishes last, because he's only swimming north at 1.7. Tarzan and cheetah tied for first. The lesson of this story is that if you wish to cross the river quickly, direct all of your energies to do so. In other words, swim straight across and don't care how far downstream you're going to get. If you just want to get there fast, go straight across. Let the current take you. Don't fight it. Tarzan used up some of his velocity in fighting the current in order to end up in a position directly across from where he started. So he had to actually use up energy to go straight across. He would get there later.
Called it.
Does that make sense? Yeah? Last example, example number 9 here. Also a stupid one. Does it say stupid in your book, Sean, on example number 9? Because it doesn't make a lot of sense. The editor didn't do a very good job here. Let me read it and we'll see if we can pick it apart. This is on page 101. A pilot with a heading of north 30 east and an airspeed of 400 flies into a wind coming from the north at 110. What is the plane's velocity relative to the ground? That's the resultant. And how long would it take to complete a journey of 1,000 kilometers an hour at north 30 east? Well, the first thing that pops into my mind is he's not going to end up going north 30 east, is he? Why not? Because of the wind. So the question is stupid to begin with. Let's just see what we can do with it, though. So the heading is north 30 east. That is the plane vector angle, right? The airspeed is 400. What do you think that means, the airspeed? That's how fast the plane is going, right? If there was no wind. So that's the plane vector. Those two things are the plane vector. The wind vector is 110 from the north, so it's 110 to the south. Let me just write wind here. I just put W, that's a bad idea. Wind is 110 straight south. What is the plane's velocity relative to the ground? So we are solving for the resultant. Is he going to end up going north 30 east? No, he's not. This part here is wrong. In fact, I would just remove that from the book. You can just stroke it out of the book if you want. Right?
The direction.
Yeah, because, I mean, he can go a journey of 1,000 kilometers, right? Okay, so let's do this by components. So let's draw our P here. North 30 east is going to be north and east. So this is our plane. We'll call this PY and PX, just because they're horizontal and vertical on our sort of page, right? And this is 30. The always entertaining Michael Paulette. PX is going to be opposite or adjacent? Opposite. So it's going to be 400. Opposite is sine. 400 sine 30. Oh yeah, they do it by stupid sine law and cosine law in the book. The question is, why do we use sine? Because we know the P is equal to 400. We know the hypotenuse, right? We know the hypotenuse. We want the opposite. What's the one that has opposite and hypotenuse? If we used adjacent, do we know what the PY is? No. You have to use the hypotenuse. So 400 sine 30 is 200. And that's to the right, so it's going to be positive. When I add components, I like to put my x in one column and my y in another column. So I'm going to put the py over here. So 400 cos 30, which is going to be 346. Also positive because it's up, north. Everybody good to there? Yeah? Okay, so the wind, which I'm going to draw in red, remember, is 110 to the south. This is the wind, and that's not red, that's blue. P, not P, wind x is how much?
110.
No. No. What's the x component of the wind? 0. There is no x component. What's the y component of the wind? Negative 110. Why do you not need an angle? Because it's straight south. And it's negative, you're right. To find the resultant, which I'll do in blue, I add my components. So I'm going to have Rx is going to be 200 plus 0, or 200. And my resultant y is going to be 346 minus 110, which is 236, right? Adding components, we now combine the components back together again. Rx is 200. Ry is 236. There's my result, right? The resultant squared is going to be 236 squared plus 200 squared. And I get an answer of, I think you guys can do the math there. I don't think I need to write it all out. I get an R value of 309.3 kilometers per hour. Not surprising, right? Why is the resultant speed less than the airspeed of the plane, 400? He's going into the wind, exactly. He's going into the wind.
How long it would take.
Well, that's the actual resultant speed, right? What heading do they take off, or what direction are they actually going? Well, that angle right there, right? Theta is going to be tan minus 1, opposite over adjacent, 236 over 200, which is going to be east, really close to 40. Oh, it's not. It's 50. I drew it the other way.
So it really doesn't matter what, like, tan, cos, whatever, like...
Not here, really, because now you know all three, right? Yeah. I just tend to use tan. It's just whatever. Yeah. Now, the question actually asks, how long would it take him to travel a journey of 1,000 kilometers? So it would just be 1,000 divided by 309.3. It would be 3.23 hours. But he would not be traveling at that original direction. He'd be traveling at east 50 north. I don't even know if the book handles that, do they?
That's what you said?
Yeah, they get the same answer in the book. So they've just basically, this part of the question where they say, here, just stroke it out, because it doesn't mean anything, right? They wouldn't actually be going north through the east. They'd be going east 50 north. I guess that's north 40 east, wouldn't it? Right? Do pilots have to do this sort of stuff when they're flying in the wind? Absolutely they do. Absolutely.
So you can be pilots?
You certainly have to be able to understand this, right? Do you think a computer figures it out for them?
Obviously.
Obviously. But if the computer goes down, the guy's got to be able to get out, the navigator's got to be able to get out a piece of paper and a protractor and a map and actually do these calculations. They actually have to do it. Pardon me?
And a pencil?
Yeah. And a calculator. Hopefully he's got batteries in his calculator. Okay. There's a few questions on page 103. You can try number 2. And 116, number 35, 36, 41, 42, and 43. By no means am I assigning them all. I'm just saying here's some problems that you can try to sort of get a good practice on this type of thing. I'm done. You got the rest of the period. Tomorrow, review time, test Thursday.
Okay, so